when I was here last year, I think some of you were here, I was talking about our goal language and how this can be used for, in that case, financial services, client onboarding. At the end of that presentation, I began to touch on an element of what goals actually mean in terms of execution. And what I wanted to do with this presentation was just continue along that track a little bit to understand or dig into our view of what an intelligent process or an intelligent process execution is. So for those that are not familiar with Whitestein, we're a smaller BPMS or iBPMS vendor based in Switzerland. We have customers on several continents now, but we're still relatively small and boutique. Our iBPMS is used in many different industries. Probably the primary one is financial services. Here I'm going to look at a case from the logistics domain. And the thesis that I want to approach here is first to ask the question, well, what's an intelligent process, or at least what's our view of what an intelligent process is? And then to ask this question, well, why is intelligent process execution, IPE, as I've called it here, an imperative? Why is it important? What is it about difficult domains or complex domains that makes intelligence, as I'm defining it, a useful thing to use? Then we look a little bit at our approach to intelligent process execution, what that means, and here you'll see something called intelligent process controller. And then we'll look at a case study from the transportation logistics domain. I've chosen this particular domain because it helps illustrate the dynamic interrelationships between processes that can govern a lot of different interacting entities. And particularly in transportation now, we see a lot of proliferation of devices. I'm going to mention Internet of Things. This is certainly something that's pushing the proliferation of individual devices which need to be considered by processes on an event-based basis. So in order to define an intelligent process, looking at the philosophy from where we came from as a company, when we were devising our ideas about intelligent process execution, the first question we asked ourselves, well, what's an intelligent person? Here's one example. So, an intelligent person is defined in rather simplistic terms by experiences, so what we observe, the knowledge, so how we convert that stimulus or those experiences into something that defines our beliefs, our understanding of the world, our understanding of what we need to do, which links into goals, so what we want to achieve. The adoption of goals becomes an intent or something that we wish to or we intend to execute, and the way in which we will go about doing that is a plan. And then when the plan is executed, it's a sequence of actions. Very, very simplistic. So we take this definition and we think, okay, well, if that works for humans, let's try and bring that across into a process execution engine so that we gain the flexibility of having a goal-directed execution. So we don't have to plan everything in advance. We can provide a set of different actions and plans and fit them together according to the objective or the goal that we want to achieve at the time. So if we now look at the intelligent process, experiences can be described as acquired data, of course. I mean, this is the consumption of information from the environment. Knowledge is actionable information. Goals are adoptable intentions, so things we intend to do or the process intends to do. Plans are the way in which we want to achieve those goals, and actions are the result of executing plans. Now, to look a little bit more closely at each of those. Acquired data, so as I said, this is stimuli from the operational environment. Of course, at the moment, there is a huge growing and proliferation of data and event sources. I indicate Internet of Things here. I'm involved with a couple of European large-scale projects involved with IoT and understanding how to manage the vast number of events sourced from domains such as logistics and manufacturing, and understanding how to consume that data in a way that makes sense when executing an end-to-end operational process. There, of course, is alongside that a multitude of different data types, which are structured and unstructured, which we're aware of. And, of course, there are large volumes of data, which is constantly changing. So all of this data is the central driving thing behind the intelligent process control. Knowledge, of course, is the conversion of that actionable that information into actionable information, that data into actionable information. So there is the information state. This describes the information state of the executing process. It's an analytical interpretation of the observed data. So this is converting the data into something that is semantically relevant to the way that the intelligent controller can understand it and use it to execute a process. Detection and analysis of patterns. This is important for learning. Learning is something that we don't have in the field with our custom deployments at the moment, but it's something we're working on bringing in, and I'll mention a little element of that later on. Semantic profiling classification and continuous revision of the process information state. So while you're executing a process, you learn more about the process and you learn more about the operational environment that process is executing in. So it's important to ensure that the belief state, as we call it, or the information state of the process is kept up to date. So goals, these are what we term adoptable intentions. Okay, now you'll see goals in an example later on. So they are operationally relevant behavioral directives, effectively. Things that the process wants to achieve. So it's an intent to be achieved that furthers the process goals. It's achieved by selection of a suitable action plan. So we have several plans that can be selected to achieve the goal. And partial or complete failure may lead to reconsideration. So that means is that you have a goal that the process wants to achieve. It tries or selects one plan using preconditions to try and achieve that goal. If that plan becomes irrelevant or fails for some reason, you may want to reconsider trying that plan again under different conditions or try using a different or alternate plan. So you can do this dynamic reconsideration of the way in which you want to achieve a goal. Then plans, of course, these are reusable action sequences. In our execution environment, a plan is simply bpmN logic, bpmN 2.0. These are reusable action sequences. They are fragments or snippets of bpmN logic that are created at model time and then are available in libraries for use during execution. They're dynamically constituted during execution, so you can build up plans from fragments as you execute. And you can select them ad hoc to meet goal requirements. And then finally, actions. They are the result of executing plans, of course. They're performed plans. Actions are performed as specified in a plan, and they remain aware of action effects. And if necessary, an action, of course, can create a feedback loop within the executing context to trigger reconsideration of the action and the effect it's had on the operational environment if required. So why is intelligent process execution an imperative? Well, for our first point here is that looking at intelligence from an analytical point of view, so deriving understanding from complex data, is only as useful as if you can convert that into a way of acting or executing upon that data, upon those observations. So because processing shifting patterns, so changing data in vast complex data increasingly demands, we argue, machine deliberation. It's not enough just to analyze data and provide suggestions to humans. We need to be able to create machines that are able to process that data and make proposals, or in fact, what we're arguing is take action automatically based on the understanding, the goal-driven understanding of how to perform those actions. And of course, as aligned with that is continuous reconsideration. It's not enough to have a goal and select a plan to achieve that goal. You need to continuously consider whether or not you're doing the right thing or whether the intelligent process is doing the right thing, and reassess and realign how you go about executing that process in accordance with the changing data environment. The second point is because effective processes adapt their structure by dynamically interleaving structured activity flow, so imperative processes, with event-triggered and ad hoc activities. This has come up a couple of times during the last couple of days, but it's a very important point there is no world where an imperative, or increasingly there is no world where there is purely an imperative action flow process separated from a data or event-driven process. The reality is, in most situations, that you need to be able to encompass both. So if you are inside an imperative process and an action is taken on data, that process needs to realign itself and adjust in order to take care of the change to the underlying data state. And we need to have a fluid relationship between the two. And of course, also because strategic governance of process-driven operations must be active, not passive. This means that it's not enough to say that a process must be in alignment with a particular KPI or constraint. There must be ways in which we ensure that policies and governance procedures that overlie multiple process instances from a strategic point of view have active control. This way we can ensure that business-level governance policies have an actual effect on the underlying executing process instances that drive the operations of the business. And probably the most important point is because it helps create solutions to customer problems. And that's effectively all we are choosing to do here. We're not trying to invent something that sounds as though it should be good. We're applying this intelligent process control to problems that require, from our point of view, a slightly different approach from the traditional way of executing processes. Not every customer, of course, uses this style of process. But for particular complex cases, like this logistics and transportation case, it's an advantage to use this form of intelligent process control, which can continually reconsider the flow of information and interaction between these complex, often independent and data-driven entities. So therefore, we apply intelligent process control to manage complex process graphs. It works on a cycle. Each intelligent process works on a cycle, observing, comprehending, deliberating, deciding, acting, and eventually learning. Also, collaboration is important. So when you have a process instance that is being executed by an intelligent process controller, which is operating around this loop, it doesn't work in isolation. It may need to interact with other intelligent process instances, intelligent process controllers that are responsible for other processes. This collaboration can be handled either by delegation, awarding, which is like a call for proposals, where you negotiate who will take on a particular task and you hand it over to the winner of a particular auction or call for proposals, or a different form of cooperation. And there are different models in which we can cooperate, take actions between different executing processes to work together to solve a particular task. So distributing work. And then, of course, learning. So an intelligent process controller, and here it says also known as a reflective agent. So this is drawn from the philosophical idea of a software agent. We don't claim it is an agent, but then there's probably no such thing as an agent. An agent is just one way to define how a particular piece of software executes. It's called reflective essentially because it has the ability to introspect on its own actions. This is the point about reconsideration. So it's constantly evaluating whether or not it's performing the process in the right way. And indeed, whether the interactions with other process instances is working in the right way. So it works on a cycle, and here you can see many of the elements that I've already described. The observation of events and data. There is a knowledge base, effectively, that the process maintains about its own data state, information state. And then there is a sequence of activities that flow through from the adoption of goals, the deliberation of plans, and deciding and executing those plans that are being selected to meet the goals. And this is a continuous cycle. Then we have the feedback loop from plan deliberation, from deciding to execute to plan deliberation when you want to intentionally reconsider the way that you're executing something to take an alternate path. So we assess the current situation. So any IPC assesses the current situation. It identifies the objective or the goal to be obtained. defined by the process that it is responsible for, determines the set of possible actions that help achieve that goal, engages the appropriate plan enactment mechanism for the present context. So this could be that it decides it must execute this, or it must take care of resolving that goal, or it can delegate that responsibility to another entity within the operational space, or it can go through another interaction mechanism such as awarding or cooperative work. And then intentionally reconsider whether a plan should be selected. So this is now the case study we'll look at briefly from the transportation logistics domain. The objective here is to transport goods orders by vehicle. So we have a solution that's used by a couple of customers in Europe, and it's effectively solving the traveling salesman problem on steroids. It's really a significant problem to resolve, and a lot of the dynamics come through from these points. So the problem we're trying to resolve is to organize the construction of trips by multiple different vehicle types, where trips are constituted by legs. Now, a leg can be a pickup and a drop-off, so every leg has a pickup point and a drop-off point for an order. So we are trying to ensure that trucks or other vehicles that are transporting these goods organize the goods in a way that makes the optimal sense. So it's packing goods in the right way, it's organizing trips dynamically, so if an order comes in while a truck is already en route, and there's space on that truck, it will be diverted if it fits within the time schedule to go and pick up that order. It'll load it onto the truck. Maybe it needs to take something off to reorder, relay out the orders inside the truck, and then continue on driving. So it's a very dynamic and continuously refined process, because a truck needs to reconsider whether it's doing the right thing at any one time. And of course, a truck doesn't run on its own. A truck has a driver. There are all of the event feeds from the environment within which I keep using the word truck, but actually we're talking about multiple different vehicles. It's multimodal. So it's planning this trip consisting of multiple dynamic pickup and drop-off legs. We have to maximize the usage of available vehicle capacity, and of course there are many different types of vehicle, whether it's a truck or a boat or a plane, but also even within trucks there are container trucks, there are liquid transportation trucks that need cleaning in between each different type of liquid that's transported and so forth. We need to dynamically balance the usage of own fleet. So in the case of this example, DHL have their own large fleet of trucks versus spot transportation, which is where you might select to use a truck provided by a third party to deliver the goods. Maybe a cross-docking of two different trucks at a hub. To minimize the number of low-load miles or kilometers driven or flown. So this is really ensuring that the maximum capacity is always utilized by the vehicle. And to coordinate the behavior of multiple locations, vehicles, and people. So it's a large coordination problem as well. And respond to the multitude of events sourced from telematics and the environment. And this, of course, is related to the Internet of Things point. And some of the event sources that we have within this particular customer are vehicle positional sensors, so GPS tracking, load status sensors, so this is sensors inside the vehicle that's saying what's currently on that vehicle by RFID tagging, for example. So you understand exactly what orders are in the truck and what space is available dynamically as orders are loaded and unloaded. State sensors, so this is the vehicle operating within normal parameters. Is it low on gas? Is there some system within the vehicle that indicates it may not be able to complete its journey and so forth? Fleet management systems, so these of course back-end application systems that are responsible for running the transportation fleet. And then a whole variety of other systems which are also providing events and interaction points for the different buildings or locations that the trucks move between or the vehicles move between. So you've got airports, ports, Hubs. Hubs are effectively interchange points or cross-dock points where vehicles enter and may load or unload or repack orders and exchange orders between different vehicles in order to continue transportation, and yards as well. Communication, we have, of course, embedded, like M2M, machine-to-machine communication units on the vehicles. Of course, personal mobile devices of the drivers and other people involved within the operational environment. We have traffic monitoring systems, of course, that are sending events in on effectively what's going on in on the road systems. Toll collection units are sending events too. And, of course, meteorological or weather information systems, all indicating we use data from all of these elements to understand whether a trip should be replanned. I mean, even in terms of potentially bad weather. So if we know that a particular place in Switzerland is likely to be affected by snow during a certain period, then we might want to reroute trucks around that in order to predict or compensate in advance from potential blockages. And toll collection units, for example, there are often long queues at toll collection points, and it's possible to reroute trucks dynamically according to traffic jams and so forth, as GPS systems in your car might do today. And this, of course, is really moving towards this whole thing called Internet of Things. These are multiple devices, multiple sources for information that are proliferating massively. And in this particular domain, there's a lot of investment from transportation providers in adding more functionality, more data sources to their trucks, to their vehicles, and connecting systems together, creating a more complex information landscape for processes to deal with. So one particular customer that we have this system deployed with, a variant of this system is DHL in Europe. This is just to give you an idea of the scale of the larger customer we have using this. So they have around 60,000 orders per day. So these are orders entering into the system that's governing this, that need to be allocated to trucks. Now remember, it's a dynamic allocation. The orders don't all come in first thing in the day. They come in distributed throughout the day. Vehicles are continuously moving around Europe. This is scope to Europe in this case. And vehicles, the whole point of the optimization here is that vehicles need to be potentially rerouted as new trips are constituted, as new orders come in, or indeed different information feeds say, well, it's not a good idea to go via Hamburg anymore, you should go in a different direction. There are human dispatchers, of course. Now, the human dispatchers are the people that are responsible for making the final decision onto whether a trip is executed or not. We are now moving into a situation with DHL in particular. Initially, they only wanted to have human dispatchers maintaining control over whether or not a trip was executed. But of course, this means there's a decision loop to be made. We're now moving into a situation where it's automated. So the system is making the decision on whether a truck is or a vehicle is rerouted to pick up alternate orders or to change its behavior in some way. So it's moving from decision support to decision making. And this is where you really need to make sure that the intelligence or the control system is working well, because if you make mistakes, then the money is very quickly lost. And this system is operating across 24 countries. On average, this system's been in operation for a few years now. It sees around 25 to 30% operational efficiency boost over not using this kind of system, and around a 12% transportation cost reduction. So this is a partial view on the system performers inside this domain. The transport order is the order itself. So this is the item that some company wants DHL as a third-party logistics provider to transport for them. The human dispatcher, of course, is the human that organizes and arranges these trips. And the transportation capacity is the vehicle. It's multimodal, so it could be a truck, it could be a boat, it could be a plane, and so forth. A warehouse is where goods are stored. A transportation hub, as I described before, is where trucks cross-dock and exchange information. And a vehicle driver is, of course, the person responsible for driving a truck. Now, each of these entities have a parameterization around them, and those parameters are changing all of the time. And part of the problem here is doing a parametrical matching between the changing constitution of each of these entities. So a vehicle driver, for example, a driver may change his behavior on a daily basis based on whether or not he has to take on other work or be away from work, unplanned schedule changes. But a small thing like a driver being unavailable for half a day might actually completely affect or have a knock-on effect on several trips, because you might need to find another driver and who then drives the previous trip. So it can have quite a complex wave effect through the system. So you need to be able to manage that, and this is partially where learning will come in here to understand patterns of behavior and how to plan around certain situations. So looking at each of these entities, the transport order, so the process executor for the transport order. So you'll see in a moment there is a process, a goal-driven process around managing an order. The process executor for this is an IPC, so it's an intelligent process controller. Its primary goals are to define the order parameters, to plan the order routing, and to execute the transport. And the interactions are primarily with a dispatcher in order to plan order to a trip. The human dispatcher, the process executor here is a human, and the primary goals are to match orders to vehicles, to produce the trip plans, and to replan on demand. The transportation capacity, again, this is an IPC now, so this is an IPC representing the vehicle. You've got to go to the order and pickup and delivery point, load or unload orders, and perform maintenance on the vehicle. The warehouse, this is a mixture of IPC and human, so you have IPC, intelligent process control, for elements of the warehouse, but of course you have human decision makers involved here as well. So schedule the vehicle arrival and departure, manage local resources, load and unload vehicles, and store orders. And the transportation hub, much the same. This is again IPC plus human, and the vehicle driver. This is the goal model I wanted to show for the. This is the human. Sorry, this is the order. I'm trying to get this to a point where you can see what it is. So it's a goal-driven process. It's using our own notation. You have order fulfillment, which is the final top-level goal that the IPC must complete in order to satisfy the execution context of this process. There's several sub-goals, two of which are executing in parallel. So this is the order reception here. This is to import an order either from a manual order point or importing it from a web channel. Then these two central plans here are responsible for planning with the dispatcher and finding a vehicle to the order. And and then down here we have the order execution. So within here, this is managed shipping. So if you go in here, there's a standard plan. This is a standard activity plan. So this is where the imperative comes in. There is a plan to be performed. It's a sequence of actions that must be executed. However, if we go within plan to dispatcher, we have here adopt a new goal. So this is an intention object is being created that is responsible, saying that the IPC for the order is responsible for planning this. And the strategy here is to delegate. So we're delegating. The order is saying, please, sending a message to the dispatch IPC controller of the dispatch process to take this order and plan it into a trip. So if we look at this is the a simplified view on the dynamic goal execution that's running at the same time. So this is running within the same context of the IPC. So each IPC, it has the goal tree that guides its normal behavior. This is what its job must be. This is what we just saw over here. This is the daily work it has to do, but at the same time there is another process running connected with this, which has, it's within the same process context, that has a to achieve goal, and there are different methods or plans underneath here in order to how to interact using that intent to either perform a local plan, and these are the different elements of how the IPC can go about solving this problem. You can either use a local plan, so this is to do it itself, select a plan and execute it within its own context, to delegate a plan to another agent or another IPC, to award a plan, so this is to execute a call for proposals, or to co-build or cooperate around a plan. And so if we go into designate here. So we have essentially a BPMN process here that is communicating to the delegatee. So you're announcing that you have an intent, some solution that needs to be found. You're asking the IPC representing the dispatcher to take care of this. And then you have some logic here that's controlling whether or not the goal was reached. And if it wasn't, you can actually reconsider the intent. So this catch here is to check whether or not the delegatee was able to perform that function or not. And if not, then you can reconsider the intent. This is the intent reconsideration process that, again, is running as part of the context of that IPC. And this is where we control reconsideration. So the main points here are that you have a set of governing policies that, depending on the control of the individual IPC, it asks the question of whether the current situation and the new event should be the current intention go on as before, or whether we should change the strategy and take an alternate route. If the answer is yes, then we deliberate within the IPC, choose a new strategy about how to execute. Maybe it's a repeat of the same method, and then invalidate the current plan. So this is the dynamic plan selection that's reconsidering the events based on either how that IPC is executing or how the delegatee or another IPC that's been asked to do the work is executing.